Should robots be taxed? I'm Pedro Teles. I'm going to go through the presentation of this paper that's joint work with João Guerreiro and Sérgio Rebelo. So should robots be taxed? So there is evidence that the rise in automation that we've been observing in the last few decades has increased income inequality by eliminating the jobs of routine workers. These are two papers on that evidence. What we do in this paper is we take this evidence, we calibrate a model to it, we extrapolate the evidence going forward, and ask the policy question on whether robots should be taxed. You can find a link to a video by Bill Gates on a proposal for a robot tax. This was partly motivation for the paper, and it's really interesting to go through the arguments of Bill Gates and compare them to the results in the model. So I'm going to go through a simple model that's static without skill choice, and we're going to solve the optimal robot tax problem and go through the intuition for the results. Then move on to the quantitative dynamic model with skill choice, where we go again through optimal robot taxation. We'll go through the calibration of the status quo economy and the quantitative policy results. So in the static model, there's two types of households, routine and non-routine in shares pi r and pi n. The utilities of consumption and labor and government spending G. And agents consume out of labor income minus taxes. Taxes are a function of labor income. They cannot be a function of the time. Robots are an intermediate input that is produced by competitive firms using fee units of output. So the price of a robot is fee. As fee goes down, the price goes down. The final goods firm uses non-routine labor, routine labor, and robots with this production function where robots and routine labor are perfect substitutes, and they aggregate and non-routine labor are according to a complex function. The level of automation is the share of robots in the total of robots and routine labor. For this firm, the cost of using a robot is fee increased by the robot tax. And because of perfect substitutability, the firm is indifferent between hiring a routine worker or using robots if the wage is equal to the cost of producing the robot, including the robot tax. The choice of the government is on the tax function, on labor income, the robot tax, and G, and markets clear when total private consumption plus public consumption is equal to total production minus the cost of producing robots. Now, the competitive equilibrium in this economy, because of the assumptions on the technology, because of perfect substitutability and constant returns to scale, we have that the two wages are functions only of technological parameters and the robot tax. As the fee is reduced and reduced possibly to zero, the wage of the routine is going down to zero, while the wage of the non-routine is going up and going up to infinity. So the wage inequality is escalating. The use of the robot tax can reverse this. So increasing income inequality that can be increasing at least wage inequality that can be reversed by robot taxes. So if there were no restrictions on how to redistribute between the two agents, then there'll be no role for the robot tax. If the planner could use lump sum taxes that would be agent specific, robot taxes or any other distorting tax would have to be zero. That's obviously not what we assume. We assume in the Malaysian tradition that the government does not observe the agent's type or variables that could reveal the type, such as labor supply. The government observes the agent's total income and can design taxes on total income. Robot taxis are assumed to be proportional. So with these restrictions, we should again ask the question whether it's optimal to distort production decisions to redistribute income. So again, the planner is looking for the optimal tax functions, but it's simpler to solve the problem if we solve for the optimal locations and at the end compute the tax functions that implement them. So when we write down that problem, we have to impose incentive constraints. This is the incentive constraint of the non-routine agent. The non-routine agent must be at least as happy with the allocation of consumption and labor hours than with the bundle of the other agent, which is it's a bundle for consumption and labor income translated into hours for the non-routine agent. There's one of these constraints for each agent. The planner problem is then to maximize the weighted average of the utility of the two agents, where the weights are the shares in the population, subject to resource feasibility and the two incentive constraints. Now, in this economy, routine workers lose from progress in automation, and the planner wants to redistribute to them. But as the planner redistributes, non-routine workers could pretend to be routine. It's this restriction, the incentive constraint of the non-routine agent, that is the relevant restriction for the planner that wants to redistribute towards the routine agents. So once we understand that, we are ready to get the first result, the result that is the basis for all the results in the paper, the more quantitative results in the paper. In the optimal plan, robot taxis are strictly positive. So in order to understand that, let's suppose that we start with 0 taxes on robots and we increase them to a positive value. Increasing the robot tax increases the wage for the routine and reduces the wage for the non-routine. As you do that, you increase the number of hours that the non-routine agent has to use in order to produce the income of the routine. So it becomes more costly for the non-routine agent to pretend to be routine. That relaxes the incentive constraint of the non-routine agent, and this has a first-order welfare effect. Now, there's a negative welfare effect from increasing robot taxes. Robot taxes distort production. But if you start at 0 taxes and you increase taxes, the marginal effect is 0. The welfare effects are second order. When you compare the two, the result is in favor of robot taxis. Robot taxis are positive at the optimal solution. So this simple static model is useful to illustrate the argument in favor of robot taxation. But it is missing important features that we need to take into account in order to obtain reasonable results for optimal taxation. One feature that it is missing is the possibility that agents may acquire skills. So we move on to a dynamic model where we allow for endogenous skill choice. The structure is overlapping generations, and an important assumption is that the workers choose the occupation when they enter the labor force, and then they cannot retrain afterwards. And again, the exercise is taking the cost of producing robots down to 0. There's going to be 2 types of households in this economy, 2 types of workers in this economy. Workers that were born before the beginning of the economy, and they cannot retrain. They have exogenous skills, and agents that can choose their skills because they were born after the initial period, having heterogeneous utility costs of skill acquisition. The production structure is for all purposes the same as in the static model. Optimal taxation. So again, also in this dynamic problem, taxes are a function of histories of income and consumption. They are not functions of type, wage, labor hours, or skill choice. Now, in this dynamic model, because of endogenous skill choice, we are going to have 2 incentive constraints. We are going to have intensive margin incentive constraints on the choice of labor supply and extensive margin incentive constraints on the choice of skills. To ways of distributing across agents in this economy. There's a direct redistribution regime that uses the income tax function to redistribute income from the non-routine to the routine. Positive robot taxes help. But this direct redistribution from between the two agent types reduces incentives for skill acquisition. There is an alternative way to redistribute in the population, which we call an indirect redistribution regime, which is precisely through skill acquisition. And for that, you need that direct redistribution is low and that robot taxes are not used. As the cost of producing robots goes down, this indirect redistribution regime through skill acquisition becomes more attractive. So we are ready for the quantitative results. So we calibrate the model to the US economy between 1987 and 2017. We use the tax function of Iscote, Storas, Latin, Violent, estimated by them. We assume that the tax on robots is 0 in the status quo. We calibrate some parameters externally. We calibrate others internally for the steady state before automation and for the transition to the new status quo steady state. In particular, we set production function parameters and skill parameters to match the path of the non-routine wage premium and occupation shares in this way. So these are already results, numerical results, first for the status quo and then for optimal policy. So here we have time from 1987 to 2080, and we have phi, the cost of producing a robot, going down over time. As that happens, automation increases, net output increases, and wages diverge. The wage of the non-routine goes up, the wage of the routine goes down. Hours don't change a lot over time for neither a type of agent. The average consumption of the non-routine goes up, and the average consumption of the routine does not go up, goes slightly down. There's divergence in utility levels. Over time, more and more agents choose to acquire non-routine skills. So what can policy do to this increasing utility inequality? So these are the results for optimal taxes. So in the first few periods, 30 years here, robot taxes are positive. They are not very high, they are modest, but they are positive, and then they become 0. They are positive while the initial old generations are still active in the labor force. They become 0 after they retire. These high robot taxes, as part of the tax scheme, including the taxes on labor income, this reduces automation initially relative to the status quo. So the solid lines are the optimal taxation equilibrium, the dashed are the status quo. But automation picks up at a fast rate under the optimal policy. Net output is much higher under the optimal policy than under the status quo, both because of robot taxes, but also because of optimal income taxation. There's wage compression as a result of robot taxes. The wages of the non-routine are going to be lower than in the status quo, and the wages of the routine are going to be higher. There's going to be divergence in consumption, and there's also going to be divergence in utility. And notice that the gap between the utility of the non-routine and the routine is going to be higher under the optimal policy than in the status quo eventually, but also initially it's not lower, it's higher. So optimal policy favors a distribution through skill acquisition. Favors more so after the initial old workers have retired, but even initially. So initially, there's more direct redistribution through the labor income tax function and through robot taxes. That is reduced after a while. Robot taxes become zero after a while, but overall, the optimal taxes favor skill acquisition. So these are the main results in the paper. I want to make an additional point. So what we've been looking at is optimal policy starting in '87, going forward. So we would have had under the optimal policy 30 years of robot taxis, and robot taxis will now be zero. But of course, if now we were to be redesigning robot taxis, we would again have positive robot taxis. I mean, the reason the optimal plan is time inconsistent. This is a common feature of optimal policy problems. This low redistribution, direct redistribution, is only optimal ex ante. After skills are chosen, the planner wants to do direct redistribution. So we can conclude with the current US tax system, a sizable full in automation costs leads to a large rise in income inequality. Policy can address this, but in designing the optimal tax system, you need to be balancing two objectives: redistribution towards those that lose from automation, but providing incentives to the end population to acquire non-routine skills. Taxing robots are useful initially in order to redistribute to the losers. While the initial old generations are in the labor force, it is optimal to tax robots. After these retired, robot taxes should be zero. Overall, the optimal plan favors skill acquisition.